This morning in North Carolina, wheels are spinning. Determination is winning. A passion is now a thriving business, and it shows no signs of slowing down. How? The power of a conversation, like the one Clint Spiegel had with First Horizon Bank about starting a bike wheel manufacturing facility in Asheville. Now it's not just talk, it's rubber meets road. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Clint. First Horizon Bank, member FDIC.
Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the Space Nuts podcast. I'm your host, Andrew Dunkley, and joining me, as always, my good friend, Professor Fred Watson. Hello, Fred.
Hey!
How are you?
Yeah, I'm well, thanks. Better than I was last week.
Well, yeah, and of course you were very, very busy doing all the Apollo 11 interviews all over the Australian media and probably beyond. It was a very busy week. And as I speak, I know this is going to come out later, but today's the anniversary of the splashdown. So
yes,
we're finishing it off in style. But yeah, it was just amazing watching all the different angles that people came up with and all the footage and those famous words again being heard. I know we've heard them hundreds of times over the years, but they were just telling moments in human history which should never be forgotten and no doubt won't be. I foresee a day where they'll probably have a little memorial or something on the moon for the astronauts many years from now, but maybe I'm wrong. Now, Fred, we've got a lot to talk about because we dedicated all of our last program to the Apollo missions and the legacy thereof, and people are still downloading that episode in droves. I think that episode in one day took as many hits as the previous episode took a week to have downloaded. So it was very popular. So thank you to everybody who grabbed a copy of episode 162 about Apollo. Today we're going to dedicate the whole program to questions because we've got a massive backlog, and I have to apologise again. Apparently people have been posting questions on the Facebook community tab that I didn't know existed. So we're going to get stuck into those. We're going to talk about rogue planets. A great question about rogue planets has been put forward. Another one about lunar orbits and returning to the moon. It's a very good question because it is one that people wonder about. Why haven't we? We'll also look at black holes. Carrie has sent a question saying, well, I heard the episode on black holes and I still don't get it. And I know where you're coming from, Carrie. She's also the one that alerted me to that Facebook issue. And we're going to talk about galaxies losing stars. How's that, is that a situation that some galaxies face? So plenty to discuss today, but we're going to start off with a question from Andrew Stacey. G'day, Andrew. Thanks for your question. Greetings from Ontario, Canada. Hey, I've been a listener for close to a year now. Always look forward to it every week. You mustn't have much to do. My question concerns rogue planets, that is to say, planets that no longer orbit a parent star and are adrift in interstellar space. I've often heard scientists talk about these types of planets existing throughout our universe, but the methods that we use to detect exoplanets involve the planet's effect on a parent star, such as the transit method or the wobble method. So my question is, are rogue planets in interstellar space merely a theory or logical conclusion that astronomers have reached? Or have we confirmed that they exist? And if so, how might we go about detecting them? Thanks, as always, for your excellent podcast. Good question, Fred. We're going to spend a bit of time on this one.
We are, because it is a really interesting topic, which I don't think you and I have spoken about very much.
I think we've brushed over it, but we've really never focused on it as a specific topic, no.
That's right, never nailed it, as it were. So let's answer the last bit first. The
You
question
always
about
do that, Fred.
Well, I'm just contrary that way, Andrew. I just can't help myself.
Because you're from the opposite end of the world. That's why.
That must be what it is, yeah. At least I don't answer it upside down. Oh, maybe I do answer it upside down. So Andrew's question, are rogue planets merely a theory or logical conclusion, or have they been confirmed to exist? And if so, how might we go about detecting them? Well, we have done. They definitely exist. They are known objects, and their detection is actually quite interesting, the fact that we can see them. Let me start off with the etymology of the term, though. Rogue planets is just one of the names given to these planetary-sized objects that don't have a parent star. Other names are orphan planets, homeless planets. The official International Astronomical Union name is sub-brown dwarfs.
Oh, right, okay. Yeah. They'd
the
come
one
up
I
with the
like
lame one,
best-
wouldn't they?
Yeah, the one I like best, though, is an acronym. And the acronym is FLOPS.
Oh,
A FLOP, it's actually got two Fs. Free-floating planetary mass objects. You've got to garble the initial letters a little bit, but they're called flops, or F-flops, free-floating planetary mass objects. And that actually describes them perfectly. They're objects with the mass of a planet, but they don't have anywhere to go in terms of their orbits. And we've known about them for probably 30 years or so. If I remember rightly, the first clutch of these rogue planets, let's use Andrew's term because that's the one I like, actually. Yeah. The first clutch of them were identified, I think, in the Orion Nebula, in the heart of the Orion Nebula, which is a star-forming region, of course, in the constellation of Orion, where Orion's sword is. It's the sword part of the constellation. So the first question, and I guess it really is the question that Andrew's email is actually aiming at. I was going to say Andrew's question, but I've already said it's a question. The first question is, how do we see them? Because planets we see by the reflected light of their parent star. And F-flops or rogue planets or orphan planets don't have a parent star. So how do we detect them? And the answer is by their infrared radiation. They're only seen in the infrared region of the spectrum. That comes about because of a combination of, first of all, they probably have a fairly thick hydrogen atmosphere. These things are Jupiter-sized objects. Jupiter, of course, is a gas giant. It's got a thick atmosphere, so thick that we never see the surface. If there is one, we don't know whether there is one or not. But that acts as a kind of insulating blanket. So if you've got a heat source inside this object, then there is, the theory is there's enough gaseous material around it to hold that heat in to some extent. Clearly, it's not holding it all in because some of it leaks out as infrared radiation. But Jupiter actually is quite a good example for this because Jupiter emits, if I remember rightly, it's 50% more radiation than it receives from the sun. And that's because of low-level nuclear processes taking place in its interior, maybe in the core, if it has one, maybe in the lower layers of the atmosphere. It's because, for example, uranium and other fissile materials are actually present in planets in relatively small quantities, but nevertheless they're there. There's uranium actually in the mantle of the Earth, so and the core too. So we know this phenomenon has happened in the case of the Earth, that this low-level nuclear fission is taking place that actually generates heat, and that's one of the contributors, we think, to the reason why the Earth's core is still hot. So you've got a world that doesn't have a parent star, but it's got low-level nuclear processes taking place in its interior, and a fairly snug blanket around it of greenhouse gas of some form or another, but not snug enough that none of it leaks out, none of the heat leaks out. And you've got something that you can detect with sensitive infrared telescopes, and that's how we find them. And the final question about this is, where do they come from?
Yeah.
And so Andrew has kind of preempted the answer a little bit. He's described them as planets that no longer orbit a parent star, and that actually is almost certainly one of the reasons why we find these things, because you've got a planet that has been formed as part of a solar system, but some event in the history of that solar system has basically ejected this planet from its solar system. We think that has happened in the case of our own solar system. We might talk about that in a few minutes, because we're going to talk about the orbit of Uranus, the tilt of Uranus. Once again, with one of the questions, I think. You're looking a bit puzzled there, but never mind, we'll get to it. So that is one method by which you might find a rogue planet, that it's not really, that it's been ejected from a solar system.
Could have been bumped, could have, there's all sorts of ways, I suppose, they could get knocked off course.
Yes, that's right. And it doesn't need to be a collision, actually, just a gravitational close encounter and lock one planet into a closer orbit in the solar system and eject the other one altogether. It's just a transfer of momentum. But I think from my conversations with pundits about this, and I must confess I haven't talked to anybody about it recently, but in a few years ago, I spoke quite a lot to people about rogue planets. And the other possibility is that what you're seeing here is not something that's formed as part of a solar system, but that is formed as part of a cluster of stars, each of which might have formed its own solar system. But at the low end of what we call the mass spectrum, you've got objects which are so small that they never turn into stars. They don't have enough gravitational energy to do that, to switch on the thermonuclear processes. So they become planet-sized objects, but they were formed along with the stars rather than being formed as a solar system around the star, if I can put it that way.
Yeah, I get that.
So,
that makes sense.
Two main theories. We don't really know which is the prevalent mechanism. I suspect it is the low mass end of the spectrum that is by far, I would guess, by far the more prolific mechanism for forming these objects. But ejection from other solar systems is probably a part and parcel of the story as well.
Yeah. Now, you said that we've known about these for 30 years. Does that mean the discovery of these rogue planets precedes the discovery of exoplanets, as in one's orbiting a star?
Yes, that's a really good point. 30 years is my guess. Let's see, that takes us back to round about 1989. It would have been about then. The first planet orbiting another star was... the first planet orbiting a normal star was detected in 1995. So it's roughly the same sort of time. My recollection is that it probably was in the late 1980s that we started finding these rogue planets. So yes, I think that might be right, that we found them before we found the ones going round normal stars.
It would seem that it should have happened the other way around. But...
Yeah, you'd think so, wouldn't you?
Yeah.
So a little bit perverse, that. And I might be wrong there. I might be getting my history mixed up. But
one thing that never surprises me is how often we're surprised by the weird things in astronomy.
Yes, that's right. Yeah, that's right. Yeah. Exactly.
All right, Andrew, thanks for the question. Hope we covered it adequately. We strive for adequacy on Space Nuts, as we've mentioned many, many times. And you are listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Now, Fred, we're going to try and bump off 3 questions for the price of 2.
Hey. Good value, eh?
Yeah, very, very good value. Now, we're going to take a question now from Judd Brown. Hi, Judd. He says, hello, Fred. Doesn't mention me. Another orbit question for you. Just watched a program about Apollo 11. Funny that. After the orbiter delivered Armstrong and Aldrin back to Columbia, it was left in perpetual lunar orbit. Yet it eventually crashed into the moon. You previously explained to me that satellites in low Earth orbit eventually get slowed down by atmospheric drag and fall back to Earth. Higher orbit satellites and debris orbit perpetually. Since the moon has no atmosphere, why did the orbiter crash on the moon? Thanks again for all your fascinating podcasts. Judd Brown, Sydney, Australia, Earth. I would have kept going, Judd. Sydney, Australia, Earth. What's it? Solar system. Go on. Yeah, whatever. Why did it crash?
A great question. So just to set the scene, yes, the orbiter, the ascent stage, as it was called, of the lunar module, it docked with the command module. Neil and Buzz climbed back in the command module, which was called Columbia, and then the orbiter was left to orbit the moon. Now, the other 5 orbiters for the other 5 missions that actually landed on the moon, Apollos 12 to 17, excluding 13, of course, the orbiter for those was actually intentionally crashed into the moon. And that was done in order to provide a known seismic signal. In other words, you've got something with an energy that you know about, and then you've got these seismometers on the moon that you've just left behind, so you can actually just check them out, make sure that everything's working, but more especially use the seismic signal to learn things about the interior of the moon. So that was a very important thing. But Judd is correct that the Apollo 11 ascent stage was left in orbit around the moon, but it did eventually crash onto the moon's surface. Now, I don't know when that happened. I was trying to find out how long it took to do that. But it clearly was not due to atmospheric friction slowing down the ascent stage, because there isn't an atmosphere. The moon does have something called an exosphere, which is a very thin atmosphere, and that may have had made a contribution to the decay of the lunar module's orbit. But just to clarify, it's not only atmospheric drag that slows things down, because there are what are called perturbations by the gravitational pull of other objects in the solar system. It's not just a two object system. So something in orbit around the moon would feel a very strong perturbing effect from this gigantic body not very far away, which is called the Earth. And so the Earth's gravity would also affect the orbit of the spacecraft and cause the decay that Judd has mentioned, that it did eventually crash into the moon, even though it was left in orbit around the moon. I know from friends who are connected with geostationary satellites around the Earth. These are in orbits which are 36,000 kilometers above the Earth's surface, so they're they're way, way above the outer atmosphere of the Earth. And yet they have to be corrected all the time because of these planetary perturbations. It's particularly in that case the pull of the moon, the gravitational pull of the moon.
So would it be fair to say that if we did nothing, eventually everything up there would crash?
Eventually, it might not crash, but its orbit would certainly change.
Yeah.
So it would be modified, and maybe eventually there would be a collision. Yeah.
Okay.
Yeah.
All right.
Point well made.
Have we answered Judd's question? I think.
Yes. I hope we have.
Adequately.
Adequate. Yes. No more than adequately.
Thank you, Judd. Okay, let's move on. This is a question from Matt DeVincenzi. I hope I got that right. I have never known so many space launches. We put tons of satellites and kit into orbit. Oh, he must be from where you're from, using the word kit. Will there ever be a time there is too much space junk that could risk launches, or one day we need a difficult cleanup project? Also, what is your opinion of why mankind has never returned to the moon? There must be a ton of projects we can do, or do you think it's a case of we've already got the T-shirt and funds are focused on more important missions? I like that line.
Yeah, there's lots of kit in orbit, or as we would say where I grew up, there's lots of tackle up there, you know. Yeah, we kind of almost reaching the situation that Matt has referred to, the time when there's too much space junk that is starting to risk launches. I mean, it's not yet. Launches are relatively safe still, but we're already at a stage where a cleanup is kind of getting necessary. And indeed, you and I, Andrew, have spoken many times about projects that is designed to reduce the space junk in orbit around the Earth. So that's something that we are becoming more and more conscious of, that when you launch a new satellite now, we know that you've got to show that there is a way of deorbiting it. So it will actually burn up and not contribute to the space junk cloud that exists around the Earth.
If only we'd thought of that at the beginning.
Yeah, it would have been good back in 1957 if we'd thought of that. That's right. Why has humankind never returned to the moon? Well, they have many, many times, but robotically, which is a much cheaper and in some ways more effective way of doing it. In a sense, Matt's final comment, which is even though it's a bit flippant, he's right on the money. Do you think it's a case we've already got the T-shirt and funds are focused on more important missions? It's more about the fact that a human mission to the moon is very expensive. It's relatively difficult. It's very challenging. It can be done. We demonstrated that in 1969. But of course, the main imperative then was entirely political. It wasn't scientific at all, although good science came from it. It was all about
winning the space race.
Yeah, fulfilling JFK's words in 1961 and winning the space race, showing that the United States had the capability to put humans on the moon and bring them back again safely. That was what it was all about. Because, you can do really good science much cheaper and much more safely with robotic spacecraft, that is what took over the missions. That's why we've not been back to the moon. The political imperative, I think, is once again rearing its head. But I think in many ways, the early 21st century is a more appropriate time to be sending humans to the moon because the technology has moved on. And as Matt says, there's a ton of projects we can do now, and that's all happening. And it will.
China is certainly looking at putting people on the moon. They are likely to be the next to go there in person. So
probably not.
Right, really?
Yeah, it's.
What changed
Trump
their minds? Hong Kong?
Trump administration has mandated humans walking on the moon again by 2024, and I don't think the Chinese would do it before that.
Okay, interesting. All right. Well, someone else might.
They might. Yeah.
India, maybe.
India's also got their sights on the moon, of course.
Okay, thanks for the question, Matt. Appreciate it. We'll move right on to a question now from Martin Hine. I'm interested in planetary collisions. I saw the impact that Comet Shoemaker-Levy had when it collided with Jupiter. Jupiter barely felt it. So I'm even more curious as to what and how Uranus was tipped on its axis, particularly given that it's not a rocky planet but a gas giant. Please explain. Now, we've been down this road before. You wrote a book about this, or partially. I mean, this was the title.
Well, it was the title of the book. Yeah, it's just one of the questions in it. Why is Uranus upside down? That's right. Well, it's not, of course. It's on its side. Although it's slightly more upside down than right way up, if I can put it that way. Its axis, I think it's 98 degrees, its tilt, which puts it 8 degrees below the plane of the solar system. So, yes, I mean, a comet, even one as well known as Shoemaker-Levy, is negligible in terms of its mass compared with a planet. It's insignificant. So, as Martin says, Jupiter barely felt it. The atmosphere certainly did. There were distinct effects on Jupiter's atmosphere when the bits and pieces of Shoemaker-Levy crashed into it. But as far as the planet was concerned, it didn't even bat an eyelid. And that tells you...
I actually heard Jupiter say at the time, "Is that all you've got?"
It is now, yeah. But back in the old days... 4.6 billion years ago, when the solar system was a wild and woolly young place, then there were planets colliding with planets, which is where our moon came from, probably because a Mars-sized object collided with our own planet. Uranus is thought to have adopted its curious tilt because of something the size of the Earth running into it. Maybe not even directly colliding with it, but gravitationally interacting with it so strongly that it changed the rotation axis of Uranus. And that takes a lot of doing. As Martin says, planets are big. So it would have been a collision or a gravitational interaction by something pretty big, something perhaps the size of the Earth or even bigger, which may in the process have been ejected from the solar system. That might be one of the after effects of the...
It could be Planet 9.
It could be Planet 9, or it could be a rogue planet that people in another solar system are saying, where did that one come from?
Yeah. Why did they do that? We don't want it.
Yeah. There you go.
All right. Very interesting. Thank you, Martin. Appreciate the question. And you're listening to the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, before we move on, I've got to send a shout out to our patrons. Of course, some people have signed up to our Patreon account, which enables them to just make a monthly offering, a modest amount to help us keep the lights on. I can only afford one light, but that's enough. I can see what I'm doing. But I do want to send a shout out to our patrons, Jack Tasker, Matthew Crowell, Tim Gibbs. They're all making fantastic contributions to the Space Nuts podcast, and we do greatly appreciate it because they're just fantastic people. Also, Chris Kowchuk, Christian Arden, I think is his name, Christian Brown, Hannah Webb, we've spoken about before. Hannah's a pilot and sent us some great photos of noctilucent clouds not so long ago, and Mark Snelson, who started the ball rolling by asking how he could contribute to Space Nuts, and that's why we set up the Patreon account. We think they're fabulous people. They're voluntarily putting money in the bank to support Space Nuts, and we really, really appreciate it. So thank you so much. It's fantastic. You are wonderful, wonderful people. And I also want to mention that we're on YouTube. So if you go to the YouTube channel, it's youtube.com/c/Space Nuts. And you can also find us on your favourite podcast distributor, which I'm sure you do, including Apple and Google and Podbean and Podcaster, and the list is long. We're just about everywhere. In fact, I do want to mention Podbean because they've been very supportive of us, and they've if you're a Podbean follower, just keep your eyes peeled. Can't say much more than that at this stage. Now, Fred, let's get back to the questions. And, of course, in reading all of that, I've lost the page. But here it is. From Carrie Brown, who gave me a quick lesson in how to navigate Facebook recently. Thanks, Carrie. Now, we did an episode recently where we talked specifically about black holes or the singularity and the physics around it and how big certain parts were, and Carrie gets all that, but she's also a little bit confused about the deep, dark stuff that is a black hole. So she asks, is it an accretion disk, not sphere, because that's just how things orbit, akin to Saturn's rings. When matter crosses the event horizon, is it still discoid? The event horizon has little matter distant to the accretion disk. So direct on, we see a black hole. Does that mean a black hole actually refers to the dark sphere as well as the singularity, and the whole black hole system must look quite different from different angles as per Saturn's rings? So I see where she's coming from. And as I said to you last time we went through this deep and dark explanation of black holes, I was still confused at the end of it. So I'm thankful that I'm not alone.
You're definitely not alone. Actually, Carrie starts her email with, "I still couldn't quite picture black holes after the recent episode."
Yes.
And be reassured, Carrie, nobody can. We really struggle to get our minds around what the numbers tell us. And of course, it's the equations that tell you that black holes can exist. And now we know, because we've seen images of them, that they do exist, or an image of them. But the reason why we can't really picture black holes is because of what Carrie said in the next sentence, which is, a black hole is an infinitesimal small dot where our known physics goes to crap. That puts it absolutely in a nutshell.
Yeah.
Because the fact is that the small dot, the infinitesimally small point, is of infinite density. And infinite density is just something where normal physics breaks down. However, you can still, even though you've got something which at its point is infinite in density, its consequences on its environment are still able to be understood. And general relativity details it perfectly, as determined by not just Einstein, but Schwarzschild, who first wrote down the equations for a black hole in 1916. So, yes, what we've got is this small point of infinite density. And the consequence of that is, as Carrie says, a sphere, which is the event horizon. And the event horizon is kind of the point of no return. Light cannot escape. She accurately says that, because the escape velocity of the black hole within the event horizon is greater than the speed of light, so you can't get out. Why is it a sphere? Because you're talking about the gravitational pull of the black hole, which is the same in all directions. It's what we call isotropic. However, it does change. The event horizon does change its shape if you've got rapidly spinning black holes. And then there's a whole different theory that refers to them. But it's still basically spherical. It's like a flattened sphere, almost, not quite, but almost becoming donut shape. But not, it's still got stuff in the middle. It's not empty in the middle.
Okay.
But then Carrie is quite right that the accretion disk, this is the disk of material that's swirling around the black hole, is a disk rather than a sphere. And that comes about just because of the orbital mechanisms of particles in orbit around something very dense, and the fact that they are rotating. So you've got, she draws the analogy with Saturn's rings, and that's a very good one, because Saturn's rings are sculpted into this thin disk by the gravitational effect of Saturn, which is right next to them. The same is true of the accretion disk. You've got this huge gravitating mass nearby, and the effect of that is on orbiting material is that it will swirl it into a disk. Now, that's quite distinct from the event horizon, because the event horizon is basically imaginary, although it is a real thing, because we can see its shadow on the brighter material behind, which is exactly what we saw with that image of the M87 black hole a few months ago. So the question is, so there's a number of questions that Carrie asks. One is, when matter crosses the event horizon, is it still basically forming a disk? And the answer to that is yes, it is. Even though we can't see it, because it's now swirling within the event horizon, it's still disk-shaped. It's very near the end of the road, however, because once it crosses the event horizon, then it's going to be sucked into the black hole very, very quickly. If you're looking directly down on the pole of a black hole, if I can put it that way, so that the accretion disk is presented face on to you, then the event horizon is what you would see. That's absolutely right. You see this. You should see a black disk, a black blob with the accretion disk glowing in radio waves, not in visible light, glowing in radio waves around it. But there are really weird things that happen from when you look at it from different angles, and indeed from face on as well. And that's because the black hole not only bends matter around it in its orbit, namely the accretion disk, it also bends light. And so you've got these really weird optical effects, which mean that in a way you can see all the way around the black hole because it's bending space around it so dramatically that you will actually be able to see material on the far side of it. And that, just makes it sound totally cockeyed, which in many ways it is.
Like a hall of mirrors.
It's almost like that. Yeah, you've got something that is full of weird optical illusions. And the great thing about the black hole image that was recently obtained by the Event Horizon Telescope is that it did look so much like the theory predicts, a very strange optical image. These things are all very hard to explain in words. And Carrie actually sent us an image of a depiction of a black hole, which actually is pretty well on the money. There is probably more bending of the light in a real black hole than is shown then, but the kind of thing that it's showing is largely significant. One final thing that I haven't mentioned is that the magnetic fields around a black hole are thought to be very important in dictating what the accretion disk is doing, because the magnetic fields funnel material out of the poles of the event horizon, or above the event horizon and below it, to form these jets that are also associated with black holes. So a very complex interplay of gravity, magnetism, and a swirling disk of material, all of which leads to very difficult physics, but something that with the right kind of interpretation and somebody better than me at explaining it, you can vaguely get your head around.
So basically her Saturn analogy is probably reasonably accurate in picturing a black hole, but if we looked at one, it wouldn't look like that.
That's right, because you'll be able to see around the back of it. Exactly.
Yeah. I like how she finishes.
That sums it up in a nutshell.
Yeah, I like how she finishes her email. Need a nap now.
Yeah.
Don't blame you. Don't blame you at all. Okay, let's move on to our final question for this week's episode, Fred, and this comes from Alex Patulny. Hi, Alex. Hi, guys. Great to listen to your banter each week. It's always enlightening. Question. Fred Watson mentioned in passing that eventually the Milky Way galaxy, and maybe all galaxies, lose their grip on their stars. Does this mean the stars drift away? Does a galaxy's gravity change over time? Could you discuss and explain how and why? Well, Alex, we've run out of time, so no, I'm kidding. There's a few questions in that one, Fred.
Yeah. In fact, it's galaxies don't really evaporate in the same way as maybe black holes do. We know black holes evaporate, but over incredibly long periods of time. Galaxies, they don't really lose their stars. Sometimes there's an interaction between a pair of stars which cause one of the stars to be given enough energy to escape the galaxy, and there are certainly a number of stars which are escaping the galaxy. We've observed them. But the main thing that dismantles galaxies is if they collide with each other. And then you get this really remarkable gravitational dance between the two that often strips away the spiral arms, But even then, usually after the collision settles down, what you've got is a galaxy which is composed of stars belonging to both the original galaxies. There would be some loss of stars because they would be ejected because of the gravitational interaction, giving them a velocity greater than the escape velocity, but most of them would stay put. So I think the how and why is that actually stars don't normally drift away, as a matter of routine. But when you've got events involving collisions or gravitational interactions, then they will be shot out of galaxies. Does a galaxy's gravity change over time? If its mass does, in other words, if things happen to it because of collisions and things, it will do. But generally speaking, the gravitational pull of a galaxy, which is very large, is pretty constant.
Okay, so would it be fair to say that, like rogue planets, which we discussed earlier, there are rogue stars?
Yeah, there are. That's right. What are sometimes called intergalactic stars that exist between galaxies. Yes.
Okay. Fair enough. All right. Hopefully, Alex, that's adequately answered your question. There is a black hole that gobbles up stars. It's called Hollywood. So I'd avoid that place at all costs. No, actually, been there, love it. It's a good place. That's it. We've covered quite a few questions. We've got plenty more to get through, but we will endeavour to do that. But thank you to everybody who's posted questions on Facebook or sent them to bytes.com or emailed them, or they're coming in all sorts of ways. It's we get rogue questions too, Fred, I might add. But we appreciate it. We really do. And hopefully we've bumped off a few this week, and more to come. Fred, as always, thank you so much. It's a great pleasure.
Great pleasure to talk to you too, Andrew, and I look forward to speaking again soon.
Indeed. That's Professor Fred Watson, astronomer at large. And from me, Andrew Dunkley, thanks again for listening to Space Nuts. See you next week.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.